Hello, everybody. This is Professor Ma, and this is the section on more on derivative as rates. Over here, what we mean by rates, you can think of as ratios. Ratios of what? Ratios of output versus input. Okay, output versus input. So the derivatives will have the, if given the function that the derivative exists, all these means the same things. And this one at prime of A is basically just algebraic calculations. And we can think of that number is the slope of the tangent line on the graph. So on the graph at a point A, and the slope of the tangent at prime of A is the slope of the tangent. And that is also the instantaneous rate of change. By that, we mean algebraically, this is the ratios of changing in the y to the change in the x, and as the delta x goes to 0. And in particular, if in the situations where x and y are in applied situation, we have units for x, and for instance, the input units x can be centimeters, or could be dollars, or could be whatever input units we want to put in the formula. Y could be whatever outputs that we are measuring. It could be how many people, it could be approximately the amount of voltage, whatever is measurable. Okay, and then these derivative will give you the rough ratio between the output versus the input. Of course, this has a unit, and the units will be corresponding to the output units divided by the input units. So we're going to use money as our first example. Okay, so let's let X be the price of an item. Later on in the example, we're going to use X as the price per chicken. Okay, and we're going to use Y as the number of chickens that can be sold, or we call that demand at the price X. So then if I multiply the price per units times how many units sold, the demand, the price times the demand, then I will get the revenue function. That's the total amount of money we are taking. So here's an example. Okay, suppose we set our chicken at $8 a piece. Then each day we can sell 120 chickens, and say do a market survey. And then now we're going to raise the price of the chickens. Okay, and for if I raise the price from $8 to $10 per chicken, now of course less people will buy the chicken. I'll find out that there's only on average 104 chickens are sold. Okay, and so from here we're going to do estimations of the relationship between the price and the demands. That is, we're going to approximate these functions. So we can think of, we have two data points at $8 per chicken, 120 chickens sold, Y is $10 per chicken, X, 104 chickens sold, Y, and calculate the slope and putting the point slope formulas, and I got these equations. So this equation is the price demand function. This tells me the price we set, and then plug it in whatever price X is, and this tells me how many corresponding chicken will be sold, the demand. Now, we're going to multiply them together since each one costs X dollars, and this many will be sold, demand. So multiply them, we get the total amount of money taken there, and that is called the revenue. Notice that's different from profit. Okay, we'll talk about that later. And so we have these revenue formulas, and now this asks us to take the derivatives, find the rate of change at when the price X is 9, means the price set at $9, and also find the rate of change at the price of when X is $20. And what does it mean? Well, here's the deal. Here is the revenue at $9. Suppose I sell at $9 per chicken and plug in the revenue formula. So this tells me the revenue will be this much. And if I sell it, if I take the derivatives, okay, and plug in 9, then I get 40. This 40 is what? What's the unit? The 40 is the units, is the output. The revenue output, of course, is dollar. How many dollar you taking? Okay, and what's the input? The input is delta X. Okay, that is a change in dollars. Okay, delta change in dollar. Okay, so it's dollar per dollar. Okay, so it's a $40 per change in dollar, change in the input. Okay, so that's the units. And what does the units mean? So basically, it says at the price of $9 per chicken, and if we change the input by $1, that is raise price $10. Okay. Roughly, we will increase our revenue by $40. Okay. So this is also called the marginal revenues in economics. So $1 change in the price roughly give you a linear approximation of $40 increase in the revenue. So if I want to make the revenue goes up, I would increase the price. Okay. But on the other hand, if I do this at when the price I'm selling the chicken at $20, and notice, and actually if I sell the chicken at $20, it's only $480 as revenues. Okay, why? Because there aren't that many people going to come in, and there aren't that many customers. In fact, if I'm here, you can see there's only 40 people, customers. Okay, and if you calculate the derivative, it turns out to be minus 136. That means if I were to increase the price from 20 to $1 more, the revenue actually is pointing down. It's going to actually drop another $136. A lot more people are going to drop down. Okay. So then, of course, when is the price that we should set? So we get the maximum revenue. And the maximum revenue, that means when the revenue is not gaining or decreasing at a point where the slope is zero, that when the rate of revenue change is zero. So we solve for the derivative upon equal to 0, and we find that it's at 11.5. So the maximum revenue is at you should set the chicken price at $11.50. That will guarantee you the most amount of income revenue we will take in. Okay. And this is not the maximum profit. It depends on how much does it cost to produce the chickens. And that's a different factors. Okay, so just want to point out the maximum revenue is different from the maximum profit. Okay, and we'll put that in the homework. So this is the rate of profit, the rate of revenue, change in the revenues versus the change in the price. Shifting $1 price, how much the revenue will change. Okay. And here is a different one, purely geometries. Okay. And we have a formula that involves the volumes of a cube, say 1 by 1 cubes, and that is volumes 1 unit, and then the surface area, the 6 sides around the cube. So the surface area is 6 units square. And then the question is, if we were to think of this cube, actually is a balloon, a cube balloon. Okay, we're going to blow it up a little bit more, so the surface is a little bigger, and suppose we blow up to the surface of the cube. Now, right now it's 6. Okay, it blows up. What's the rate of growth if I increase roughly 1 more units in the surface of the cube? We want to find out the change in the volume. Okay. And then the question says, suppose the cube is very, very big. It's 100 by 100 by 100. Again, we blow up by 1 more units of the surface. How much the volume change? Okay. So what we want is the ratio of the volume change. Suppose I change the surface. So I want the formula of the volume in terms of surface. So what's volume? Volume as a cube is x cubed. So we're going to and the surface 6 times x squared, where x is the side of the cube. I'm now going to relate directly the volume and surface and bypassing the x's. So the way we do this is we usually solve for x, we solve x in terms of v, then we plug it into the other one. Okay, so in this case, what I did is I solve x in terms of the surface. And so in terms of surface, this much, and we're going to take this value and plug it in cube, and instead of x, we're going to cube that. So those are 3 half powers. So this is the volume in terms of surface, a direct numerical formulas. Take the derivative, dVds. Okay, then the question asks us to evaluate when the surface 6 versus the surface 600. That's the 100 by 100 by 100 cube. Okay, so this is a direct algebra calculation. I'm going to let you do the cleanup of where the coefficient comes out to be that, and plug in 6 and go get 1/4 and plug in 600. We're going to get 2.5. So this I'm going to you can verify these. Okay. And what does this say? Okay, so this says that 2 different. You can also interpret this as dV is equal to 1/4 ds. Okay, when s is 6. This is a differential form. dV is equal to 2.5 ds when s is equal to 600. Okay, and this says when at surface equal to 6, and if I change ds, think of ds as delta s. Okay, and we can set an approximate one. So basically, the volume is a quarters of the measurement change in surface when s is equal to 6. However, when the surface is a lot bigger, 600, a cube is a lot bigger, and then the volume will be 2.5 times of the amount, the surface increment. Okay, so for a very large cube versus a very small cube, okay, and if I were to blow this out, so make it slightly bigger, so, and the same thing, blow the little one out, make it slightly bigger, and so each one is the surface increased by 1 surface units. The volume expanded inside are dramatically different. For the large cube, the inside volume will be gained will be a lot bigger than the small blue cube. Okay, so this is the rate of change, the ratio of change in the volume versus the surface change. Okay, so this is basically what we can conclude. This is actually kind of interesting because this formula I can easily because I can interpret this as actually, you know, kind of loosely as delta S, as long as now them 0, I can then use this notation. I can say delta S. I can solve for delta S in terms of delta V. It's going to be delta V and 24 S times 1/2 times 6/1/2. Okay. So this formula can easily give me the change in the surface in terms of changing V. So now if I say, okay, I change the volume, I'm blowing more air into the cube, so 1 cubic centimeter, so there's more air in there, then what's the corresponding surface area of the cube change? So this differential can be easily manipulated one into one or in terms of the other. This in life science has an interesting consequence, that is for large animals, okay, versus a small animal. The small animal, the volume versus the surface of the small animal, okay, it's a very small numbers. Okay, you need a lot of surface area to enclose a little bit of volumes. The ratio, in terms of ratios, against a large body animal. That's why a small animal has to constantly scurry to look for food, to regenerate the loss of body heat, because body heat loss is related to the body surface. Okay, so we can look at Bergmann's law in biology. Okay, interesting. Here's another related rate between geometrical measurement. This one is the rate of change between distance versus angle. Another, again, we demonstrate this rate of change could be any units against any other units, as long as it makes sense. Okay, and so we have balloons going up and express the height in terms of the theta, angle of elevation, or angles of looking up as a balloon going up. And what is a unit of rate of change? Okay, and what's the rate of change when the angle is precisely at pi/4 or 45 degrees? Okay, and so this is basically the tangent relationships. And the rate of change is the rate of height change, delta high, delta H, you know, when changing the height, go from here to here is delta H, if suppose the balloon goes up to there, versus this change in the angle, delta theta. Okay, so it will be, height will be in meters, theta's measured in radians. So this is the rate of change, dHd theta, the units. And the rate of change when pi/4, we're plugging pi/4 in secant square theta, and you find out that's 2. So you find out, therefore, when the angle is pi/4, at that elevation angles, for 1 radian of increments, approximately gain is in height. So if this goes up by 1 radian, okay, of course, these are approximations, right? And basically the amount of height gain is 200 meters. Okay, this is delta H. Okay, that's what this is saying. Of course, we're not going to use 1 radian to approximate this, how much the height weighs. We're going to say, use this formula to approximate how much height when the change is 1 degree, for instance, but very little bit. And so 1 degree, you have to put in radians, that's pi/180. So you use pi/180 and multiply to 200 meters per radian. Then, so this basically is supposed the elevation change from 45 to 46 degrees. Roughly, the balloon goes up 3.5 meters. Here is something another example. This is something in physics that shows us we have this so-called inverse square law. Okay, And this is occurs a lot of places, for instance, in gravitations, in light intensities, in explosion energy of explosions, or even spray paint. Okay, as and all related to this geometrically based law. Okay. And basically, it is in this form, y is equal to something, some number divided by, so that's why we call this inverse square rule. It's the x squared is in the denominator. Okay. A lot of time x is the distance, right? Usually x is the distance. Okay. So for instance, this is the intensity, law of intensity. Okay, then so in physics, and how do we, what's the unit for intensity? Well, we measure in so-called foot candles. Okay, we can look up one in physics, what are foot candles, how bright, how intensity it is. Okay, and x is the distance. And then, if we move the light source further and further away from an object, or the object further away from the light source, then it gets dimmer and dimmer, then the intensity of the light drops. That intensity is following this inverse square law. Okay, so if we move the distance to 2, it's one quarters. And if we move to 3, this is 1/9. And notice this is the same as gravitational law, okay, and energy scattering laws, okay, and the same thing as the geometrical, the light scatters. This is basically, if we have an energy source expanding outward, okay, as in three-dimensional space, and then at a particular area that's distance x from the source and versus distance 2x, and that amount of energy on the original at distance x on the surface is going to be scattered into 4 pieces, square, 2 square. If it's 3 times as far, that is scattered into 9 pieces. This is just basic 3-dimensional rules. Okay, so hence the respective energy has to be scattered as 1/4, 1/9, etc. This is where the inverse law came from. So here, suppose we have a light source that's casting the light intensity at 12 over x squared. And then we have a screen that's 2 feet away, and then say how strong is the candle, the intensity of the light. Well, plugging 3, 2, I mean, it's going to be 3-foot candles at 2 feet away. Okay. Now I'm going to calculate the rate of change if I were to move the objects, okay, a little closer from 2 foot. How much more brighter will get? Okay, you take the derivative of the intensity of the light versus the distance, and you want to find out the amount of change intensity at 2 feet when x is 2 feet from the light. So here's a light, okay, and here's the objects, and here's 2 feet. And we're going to move these objects 1 inch or 1/12 of a foot. Okay, how much brighter will it be? Okay, so when you plug in these numbers 2, x equal to 2, and dx to be 1 inch, which is minus 1/12 of a foot, it goes closer. And you get 1/4. What is this unit for 1/4? Well, that is foot candles over per foot. Yeah. Okay. So this is, sorry, this is actually, this is the foot candles. And this one, This one was the units in foot candle per foot, and over here the foot and foot candle. So the 1/4 just 1/4 foot candle. Move 1 inch, roughly the intensity of light increased by 1/4 foot candles. Okay, so that's it. So until next time, bye bye. Adios.